applying this theory. What this is a way, as Jeroen said, of trying to image the mantle like this one. And there are a lot of questions. I'm sure you've all seen images like this, and there are a lot of questions about these that we would like to know. Basically, we just would like to make these pictures sharper and clearer. And there are two things that prevent us from doing that. One is that just imperfect geographical coverage, particularly in the southern hemisphere, and there are a lot of people in our community who are trying to improve this by doing things like US array and permanent seafloor observatories. The other thing, which is what I want to talk about today, is this, that there are some intrinsic wave propagation effects that are ignored in most present-day inversions, and that if you want to try to make sharper images, can be important. So this is something I'm not going to be talking about. The holy grail of seismology would be to know enough about the interior structure of the Earth and know enough about every earthquake that occurs to be able to fit every wiggle in every waveform. And we are a ways away from that now, although the person who introduced me, Jeroen, is getting close, as you can see here. But I'm going to be talking about something much more rudimentary, travel time tomography, which is where you measure the travel time shift between an observed waveform and a synthetic, from going from some source to some receiver. And you measure a lot of these and try to infer the interior heterogeneity of the Earth. And the main way, this is actually the workhorse of seismic tomography. This is the way most people do seismic tomography. Oh, I forgot to start my clock here. This isn't good. This is the theory that essentially everyone uses to invert travel time data. It's called ray theory. And what it says is that it relates this travel time, this observed travel time residual, to the interior structure of the Earth. And it says that the travel time residual depends only upon the structure along the ray. And basically, if you go through a slow region here, then that slows things down. If you go through fast regions, it makes things speed up. And that gives you a travel time shift. And it's just an integral along the ray. And the way this is applied, of course, is you use lots of paths, because if you just have one measured travel time delay here, then you can't tell if it's due to a slow blob here or a slow blob here. But if you also have an earthquake here and you see no travel time residual at this station, but you see a travel time residual at this station, then you can say, okay, this blob is here. And that's what people do, except people use lots of paths, up to 1 million in present-day studies. Well, there are two things wrong with this. One is shown here. This ray theory makes the prediction that if you have a slow blob here and you have a geometrical ray that misses it by 1 micron, then it will have no effect whatsoever on the travel time at this station. And that's clearly ridiculous. Real waves have finite wavelengths, and they are able to feel the three-dimensional structure of the Earth off of the geometrical ray. The second thing that's wrong with it is a little more subtle. The premise of ray theory is that if you do go through a slow blob here and get slowed down a little bit, then by the time you come out over here and are recorded at a seismic station, you remember that you went through this slow blob here. My colleague at Princeton, Kusnolet, calls this the central paradigm of seismic tomography, because it's really critical in inversions because of the way that you use these crossing ray paths in order to reconstruct your image. So that if some of these ray paths actually forgot that they went through this blob, then obviously tomography would not work. And the fact is that real finite frequency waves do forget. Here is an example of this. This is a numerically computed three-dimensional wavefront that was detonated by a source down here off the bottom of the slide somewhere. And I guess I'm supposed to put this like this, aren't I? Does that fit? Yeah. And so it's detonated off on this side of the slide. And this is the expanding wavefront that you see going out here. And right here, it goes through a slightly slower region, slower by a small a percent or so. And after it goes through this region, you can see that it's been slowed down. And this black line here is just a spherical wave, a spherical surface to guide your eye, and you can see the wave has been slowed down. But then it keeps propagating through a homogeneous medium, and by the time it gets up here, it's pretty much forgotten that it went through this slow region here. And this is just a real effect that's essentially a diffraction effect, an interference effect, that real waves do this, and it is not accounted for in ray theory. So what we have been working on at Princeton for the past few years is to get rid of ray theory, and instead we have been seeking the most general way of representing travel time residual in terms of the three-dimensional structure of the Earth, the most general linear formulation. That's, of course, of this form, and instead of using a one-dimensional integral along the ray, this is a full three-dimensional integral over the entire Earth. And what we want to know is what this so-called sensitivity kernel is that tells you how sensitive a measured travel time is to the three-dimensional velocity perturbation at every point x in the Earth. So how do we figure this out? How do we figure out what this sensitivity kernel is? Well, it's a two-step procedure. You first have to figure out how to express the travel time shift in terms of the perturbation to the waveform. So the perturbation of the waveform is, as a function of time, just the difference between the observed waveform and some synthetic waveform that you have, that you're able to compute. So you have to do that first, and then secondly, you have to figure out how to express the perturbation in the waveform in terms of the perturbation in the wave speed. So to do the first part of this two-step procedure, you have to ask yourself the question, what do you actually mean by the travel time of a finite frequency wave? And what we mean is illustrated here. We mean a travel time that is measured by cross-correlation with a synthetic seismogram. So what you do is you have a synthetic seismogram, in this case a dotted seismogram, and you shift it until it gives the best least squares fit to the observed waveform, and you measure how much you have to shift it. And there are many groups now around the world that are doing this on a regular basis and measuring cross-correlation travel times using broadband seismic data. Here is an equation that expresses this cross-correlation travel time measurement. You want to ask how much delta t do you shift your synthetic waveform in order to maximize the correlation with the observed waveform. So what you do is you linearize this equation, and when you linearize it, you get this relation here that tells you how the travel time residual is related to the perturbation in the waveform. So that's the first step. The second step is to figure out how the perturbation in the waveform is related to the perturbation to the Earth model. And this is what the Born approximation was invented for. The way the Born approximation works, you start with the equation of motion that tells you how to compute the response S to an earthquake in an unperturbed Earth model. And this is some operator that tells you how to do that. And then you ask the question, suppose I perturb this Earth model, I perturb the P wave velocity and the S wave velocity by some amount. Well, then you have to solve this equation with a perturbed operator and a perturbed response and the same earthquake. And what you do is you subtract this equation from this equation and then solve the resulting equation, and you get this expression here, that closed form expression basically for the perturbation in the waveform. And then the thing that makes this the Born approximation is you throw all these higher order terms away. So, and you put these two things together. One of them comes from the Born approximation, and the other one comes from the fact that it's a travel time measured by cross-correlation of an observed and a synthetic. And you take this expression and put it up here, right there, for that expression, and then you rearrange terms a little bit. And then you make a couple of other approximations that I'm not going to tell you exactly what they are. And you come up with an expression for this sensitivity kernel. So this is the thing that expresses the three-dimensional sensitivity of a travel time to every single point within the Earth. And it's a simple enough thing that you can fit it in one little box here. One of the most important things that shows up in this formula is this travel time difference here that I call capital delta T, and that, if you want to know the sensitivity at this point here off of the ray, then this delta T is the time it takes to go to that point and then go to the receiver minus the time it takes to go along the ray. So it's sort of this extra little detour time. And you notice that that shows up multiplied by the frequency, and this accounts for all these interference effects that are causing wavefront healing and diffraction and other things. So here's this expression again. I just kind of boiled it down a little bit. The other thing I want to point out is that this expression for the three-dimensional sensitivity has this term here. This term here is the power spectrum of your source pulse. So this is just a reminder that this is the travel time of a finite frequency wave, and it depends on maybe you put it through one instrument with a short period passband or another instrument with a long period passband or something like that, and you basically this accounts for that here. The other thing I want to point out is that if this term here, which I haven't even told you what it is yet, is 0, but this term here is 0, it turns out, for a reflected wave or a turning wave, then in that case, what you have here is an integral over all frequencies of sine of omega times this detour time. But the detour time is 0 for that point, because to get to that point, you just go down there and then you just keep going, and there's no detour. And that tells you that the sensitivity is going to be identically 0 everywhere along the ray. So here's a picture of one of these three-dimensional sensitivity kernels. This is a shear wave kernel with a characteristic period of about 20 seconds. And the earthquake is here, and the receiver is here 60 degrees away. This is a ray plane cross-section showing the sensitivity. The dotted line is the geometrical ray, and you see that absolutely everywhere along the geometrical ray, the sensitivity is identically 0. In fact, the sensitivity is kind of in this banana skin around the ray. So if you slice this through here and look at it with the ray coming at you, then you see this donut-shaped sensitivity. So when we first figured this out, we started calling these things banana donut kernels, and that's what we still call them. Now, the banana, I would say, makes sense. A finite frequency wave is going to feel off of the ray, and it feels out, and we figured out basically how far out it feels. The donut doesn't make any sense at all to a seismologist. We're all taught that when you first take Seismology 101 that travel times are only sensitive to the velocity structure along the ray. Well, the fact is they have no sensitivity to the velocity structure along the ray whatsoever. It's extremely unusual. It probably would have blown Harold Jeffries and Keith Bullen's mind. And this is an attempt to try to explain why this is true. If you have a heterogeneity right here on the ray, then what that will do is give rise to a scattered wave, but that scattered wave will come in at, here's the little scattered wave, that scattered wave will come in at exactly the same time as the background wave. So all it'll do is make a pulse that has a slightly different amplitude. And in fact, a heterogeneity there will affect the amplitude of the wave, but it won't affect the travel time. On the other hand, if you have a heterogeneity here, that'll give rise to a little pulse here that's a little bit later. It'll come in later than the background pulse, the pulse that's actually traveling along the ray, and that'll give you a waveform that looks something like that. And then if you cross-correlate that with a synthetic, you'll get a travel time shift. Here's a nice theoretical feature of these three-dimensional kernels. If you ask the question, suppose that the heterogeneity structure is very smooth, and so smooth that you can, if you write this This three-dimensional integral is an integral along the ray and then an integral in the two cross-path directions. Suppose it's smooth enough that you can take it outside of the integral in the two cross-path directions, but leave it inside of the integral along the ray. In that case, you're left with an integral here that's basically it's that integral is the cross-sectional area of the kernel. So it's like the area of the donut. And the area of the donut is something you can compute very easily. It's just -1/c. And so in this limit, you recover ray theory. So you can make the statement that these kernels are the natural finite frequency extension of ray theory, and in the ray theory limit, they reduce to ray theory as they should. What's going on here is that if you have a very small heterogeneity, then it can actually hide inside this donut hole, and it'll give you essentially no travel time anomaly whatsoever. Whereas if you have a big fat blobby anomaly like this, then basically when you take this big fat smooth blobby anomaly and multiply it by this kernel, you recover ray theory. Because even though the kernel has a complicated shape, its integral is basically what gives you ray theory. This is just making the point that this three-dimensional sensitivity is actually a relatively easy thing to compute. It turns out what you have to compute, I've written it in a slightly different form here than when I showed you before. What you have to compute is this thing here, which is the travel time Hessian. And that's something that you can compute with a single so-called dynamical ray trace. So all you have to do is one dynamical ray trace. And as a result, you can then find this kernel actually quite efficiently. So this is an easy thing to implement in a tomographic inversion. What you need to do in a tomographic inversion is you need to find this matrix here that relates changes in your Earth model to your data in this case being travel time residuals. And in the very simplest case, which is not actually what we're using at Princeton, but in the simplest case where you parameterize your model as a bunch of cells and you say the velocity is constant within every cell, then in ray theory, the way you fill in this matrix here is basically the ijth element is the length of the ith ray in the jth cell, essentially. And in this banana donut theory, the ijth element is just the integral over the jth cell of this 3D kernel for the ith ray. Now here's a nice feature of this. It actually improves your geographical coverage. If you're using rays, then you've got all these skinny little rays going through the mantle, and there are lots of places they don't see. But when you take account of the actual sensitivity, which feels off of the ray, then you've got these big fat bananas that you're filling the mantle full of. So you get this freebie. I want to show you a few pictures of what these kernels look like. So I'll show you kernels for these kinds of waves here that you can read. All of these kernels are for the Prem background model, and all of these kernels assume that the source pulse is this strange thing here. That's because we're collaborating with Guy Masters at Scripps, and this is the way he makes his cross-correlation travel time measurements for historical reasons. It's a very unusual thing that he does. He takes every single instrument, he deconvolves it, gets ground displacement, reconvolves it with the instrument response of Albuquerque, so everything looks like Albuquerque, and then he cross-correlates. You'll have to ask Guy why he does this. but as long as you know how you make the measurement, then you can design your kernel, and that's what we do. So here are a number of remember these are three-dimensional objects. Here are a number of slices through the kernel for for an S wave. And this is the ray plane slice that I showed you before. These are a number of slices just at different places across it. And these are sort of like banana split slices where you slice the banana lengthwise. Here's the 3D kernel for an SCS wave. And just a number of different ways of slicing through this thing. This SCS kernel looks like a folded banana. So you take a kind of funny banana like that and you fold it up on itself. And before you fold it, it's hollow because there's no sensitivity along the ray. And so it's still hollow after you fold it. And so right down here on the core-mantle boundary, there's zero sensitivity at the bounce point. This is the kernel for an SS wave. Just a lot of different ways of looking at it. These are all slices through it in this direction. This is the ray plane slice here. These are slices that are at different depths. And so all you should see from this is that this thing is really strange and complicated looking. Why is that? Well, it's because of the fact that PP and SS are not like both turning waves and reflected waves. PP and SS are not least time phases. They're what are called minimax phases. That means that along their path they've gone through a caustic. A caustic is a place like this where a little ray tube closes down on itself. And whenever a wave passes through a caustic, like this one here, it undergoes a pi over 2 phase shift. And so that's just something that all seismologists learn, so that if you have a nice impulsive-looking P wave, then it turns out that PP always looks kind of squirrely and emergent because it's been pi over 2 phase shifted. It's basically a pi over 2 phase shift of this waveform here. And it's because of the presence of these caustics that these kernels look funny. And it's because of this term here that I didn't really tell you exactly what it was, but what this thing is it's basically a counter that counts how many times you've gone through caustics in a kind of a complicated way. And it turns out that if you take this term into account, then it turns out that from here to here, this thing here is a sine. From here to here, it's a cosine, and from here to here, it's a sine. So you get this sort of 3 sausage link kernel, and the sensitivity is 0 along the ray from there to there. Here it's actually maximally sensitive along the ray, and then here it's got 0 sensitivity along the ray. Here are some pictures that show what happens if you slice this kernel across the ray at the point indicated by the dot. And so if you're near the source, it just looks like a typical kernel, a donut, basically, like for a P wave or an S wave. As you go toward the receiver, oh, actually, one thing I didn't say. This point here is the source to receiver caustic, but it turns out there's reciprocity going on here, and so you also end up with a squeeze-off point like this at the receiver to source caustic. And so here, this dot here is moving toward the receiver to source caustic, and you see that it gets kind of flat looking. When you get really near the caustic, it's really flat looking. This is then when you go through the caustic, and then it flips out into this sort of saddle-shaped thing. So it's a very complicated way in which the PP and SS kernels feel off of the ray, but it's just all because of the presence of these caustics. And it's also associated, the reason it has this real funny saddle geometry near the bounce point is because of the fact that PP and SS are mini-max phases. So that if you're interacting with this is a slice, a horizontal slice through the kernel, and if you're interacting with a scatterer here or here, you come in faster than the direct arrival, whereas a scatterer here and here, you come in slower. And likewise, this is a slice, a vertical slice perpendicular to the ray, and you see the slow and fast regions there. So PP and SS are really complicated, but they're not any more difficult to compute than P and S. Another kind of measurement that's very commonly made and used in a lot of tomography by a lot of people are what are called differential travel times, where you measure not the travel time of a wave with respect to some synthetic, the absolute travel time, but you measure the differential time between 2 different phases. So here are a number of different geometries where people like to do that. This would be, for example, the kind of thing that you could do if you had US array. And we can also compute what the kernels look like for these differential time measurements. And so you go back to scratch and you start with this equation, and what you want to do is maximize the cross correlation between a shifted version of waveform A with waveform B. And you want to cross correlate these two, and you can derive a sensitivity kernel that expresses the change in this differential travel time in terms of the three-dimensional heterogeneity of the Earth model, and you go through the whole same 9 yards with the Born approximation and everything, go through everything, and it turns out, in the end, you get this really simple and intuitively clear result that the differential travel time for a B minus A measurement is just the difference of the B and A kernels. So all you have to do is subtract the kernels. So, oh, yeah. There's one thing I didn't say that. There's a caveat here. It says all you have to do is subtract the kernels if the pulses have the same shape. And in the case of PP and SS, they don't have the same shape. If you want to do a PP minus P, a differential time, then this thing has been pi/2 phase shifted relative to this, and you would get a lousy travel time measurement if you just cross-correlated them. And so what everyone always knew this. So what you do is you apply a pi/2 phase shift to either one or the other yourself. That's called a Hilbert transformation before you do the cross-correlation. And so in this case, this is from a paper by Guy Masters, with whom we're collaborating. He actually does it backwards than I would do it. He actually, I don't know why he does this either, but he Hilbert transforms the P wave so that it looks emergent like the PP wave, and then he cross-correlates. And then here you see here's the way the way these line up. But as long as you do that, you can use these sensitivity kernels. So here's an example. Here's the kernel for a P wave. Here's the kernel for a PP wave. And then if you have a PP minus P time, you just subtract this from this. And so you get a red PP kernel and a blue P kernel. And this is then the sensitivity kernel for PP minus P. One of the things that these kernels are really good for is if you want to do an inversion where you mix data from different data sets that have different frequency characteristics. So here are two examples where you might want to do that. You might want to mix ISC travel times, which have a characteristic period of about a second, with the kind of long period travel times that people measure by cross-correlation. Here's something else that people really have tried to do, which is figure out what the ratio is between P and S. And this is basically a formula for how fat the kernel is, how much it feels off the ray. And it's actually very simple. This is it's called the Fresnel zone. It's got a name in optics. But you basically take the wavelength and multiply by a long ray distance and take the square root, and that's basically a measure for how far you feel off the ray. And so here's a couple of examples. Here is, for example, what the sensitivity looks like if you have long period P waves, like the kind that Guy measures by cross-correlation, and you want to combine that with ISC P wave times. And you see that the ISC P wave times are about a factor of 10 or 20 shorter in period, and so the kernel is narrower by a factor of square root of 10 or 20. And then here is a comparison of the kernel for a shear wave and for a P wave along exactly the same path. And so people who are trying to measure this ratio of P to S heterogeneity, they know that they have to be very, very careful about taking the data taking very consistent data sets so that you are still along the same ray path. But even so, you have to deal with the fact that the P waves have longer wavelengths and they're able to feel off the ray differently. So they're sensing the mantle in a different way. And we actually think this might be quite important in terms of trying to measure this ratio. My timer never started. I don't know how long I've been talking. Okay. The main thing that we've done is we have developed a linear theory. We've certainly ignored any kind of nonlinearities. We've developed, I would say, the most general linear theory, but it's still linear. And as in any inverse problem, you have to ask the question, is linearity any good? Linearization any good? And we've done a lot of work to try to look into that. And the way we do that is we compute ground truth seismograms in 3D media using a pseudospectral method, and we're doing this for acoustic waves instead of elastic waves. So we actually solve these equations in 3D for various kinds of heterogeneities. We get synthetic waveforms, we measure the travel times by cross-correlation, and we compare them with various theories, both ray theory and these sensitivity kernels. And The background medium in all of our calculations is a homogeneous medium so that this banana becomes a cucumber. It's just along a straight ray. So here's the first kind of study we did. We just put one fast or slow blob in the middle of this cube, and we propagate a three-dimensional wave through it. I already showed you an example of that. And we vary things like how big the blob is, how fast or slow it is, and where the geometry of the sources and receivers. So here's an example of one of these blobs. Let's see, this is a slow blob. And it is a slow blob that is slow enough that the path that goes immediately right through the middle of the ball would have a 6-second delay. And this is the case of a large blob with a 6-second delay. It's 8 wavelengths in radius or diameter, I forget which. And this is a small blob that's 2 wavelengths instead. And you see that in the case, and this is, as you go down here, this is the scan angle basically, whether you're looking straight through it or off to the side. And you see that when you're looking straight through it and it's a large blob, then you get the full 6-second delay predicted by travel time. But this is a small blob that ought to have a 6-second delay according to ray theory, but instead you can see that it has essentially no delay at all. So this is this fat man, little boy thing going on again. And here's another example. This is at receivers that are back of the ball, and this is the scan angle, and this is the case of the 8 wavelength ball, and you see that. And let's see. So the observed the triangles are the just observed travel times. That means we take the waveforms, we measure the travel time by cross correlation, and the thing called Born are our 3D kernels, and the thing called Fermat is ray theory. And here you see they all agree very well with each other, but then as the ball gets smaller, the kernels still do a very good job of predicting the measured travel times, but ray theory starts to do a very poor job, and here it does a really poor job, but the kernels are still very good. This is an attempt to show you how this kernel accounts for wavefront healing. It's a little cartoon, kind of. The idea is that suppose you've got a blob here that's either fast or slow. And if you measure the travel time, and here's your source here. So the blob is always a fixed distance from the source. And if you measure the travel time right after the wave has gone through the blob, then you're doing the integral of this kernel with this blob. And the blob doesn't fit in the hole at all, so you'll get a big travel time. But then if you have this receiver here after the wave has gotten this far, now the blob fits in the hole a little better because the hole is getting bigger. And if if your receiver is way down here, now the blob fits in the hole really, really well. So it's the existence of the donut hole that accounts for wavefront healing. So here's an example of this with what the waveforms look like. This column here are the unshifted waveforms, and then this is when we shift in order to maximize the cross correlation. And this is right behind the ball, and then as you go down, this is farther and farther away in the wake of the ball, basically. So right behind the ball, you see you get the full 3-second either advance in the case of a fast ball or delay in the case of a slow ball. But then as you go farther away, this heals, and you don't see the travel time shift anymore. And here is this healing plotted up as a function of distance behind the ball. So this is the total travel time measurement here. And so according to ray theory, as soon as you've gone through the ball, you remember that you went through it forever. And what the real travel times look like is you get the ray theoretical travel time right behind the ball, but then it heals with time, as predicted by the kernels. So you can kind of see from these simple one ball examples what the implications of this will be for tomography. Suppose the mantle's full of balls that are this size, 4 wavelengths, and when a wave goes through one of those balls, it will make a travel time pattern behind it that looks like this. But For a ball of that size, ray theory predicts that the travel time anomaly ought to look like this. So if you are inverting this data using ray theory, then you will end up with a recovered anomaly that is about a factor of 2 too small. So the real thing it'll affect is the amplitudes of the anomalies. You see that ray theory certainly predicts that this travel time anomaly is in the right place, so you'll get your anomalies in the right place, and it actually is almost the right width, so they'll be about the right size. They'll be a little bit fatter, but what really happens is they're going to be substantially reduced in amplitude. So this is the one bowling ball case, and we've been unable to convince our more skeptical colleagues that this is a very realistic model of the mantle. So we have also looked at 3D random models. And 3D random models look like this. You start with a cube full of white noise, and then you filter it, and you can make 3D random models that look like basically anything you want, depending on how you filter it. And so we make lots of different models like this, and we then propagate waves through them using a 3D wave equation solver and measure cross-correlation travel times and compare them with various theories. And here's a little snapshot of a wave going through one of these models. So the wave got detonated here, and after 125 seconds it's made it out to here and still looks like a pretty spherical wavefront, but by the time it's got out here, it gets these corrugations in it, and those are the travel time anomalies that people measure and do Mantle tomography with. So here's some waveforms. The dotted line is always the synthetic waveform, and you see that you get travel time shifts, and we measure these travel time shifts by cross-correlation. And then, in this case, what we do is we take the measured cross-correlation travel times, and we do scatter plot comparisons with the theory. So here's an example of one of these for a particular medium with a particular scale length, a particular RMS perturbation, etc. And every one of these plots on this axis is the measured cross-correlation travel time, that's ground truth. And on this axis is the theory. And in this case, the theory is ray theory, and in this case, the theory is these 3D kernels. And so you should certainly agree with me that the 3D kernels do a lot better job of predicting the measured travel times than ray theory does. Let's see, this is at different distances of propagation. And the other thing you see from this, we fit a red line through the scatter plot, and what you see is that all of these red lines have a slope of less than 45 degrees. And this is the signal in this kind of an experiment of wavefront healing, because that tells you that ray theory systematically overestimates the travel times. And this is, again, this healing phenomenon. Ray theory thinks that waves always remember every place they've been, and they actually forget. So the diagnostic of wavefront healing in one of these random media experiments is the slope of this line. And the way to organize the data that we collect in a numerical experiment like this is in terms of this ratio here. This ratio here is the size of a typical blob divided by the size of the donut hole. And so this is a measure of how easily a blob of a given size can fit inside the donut hole. I think this is obviously the right parameter. I think this thing probably has an official name in optics, but I don't know what it is, and we call it the donut hole parameter. So here is a plot of this diagnostic of wavefront healing. That's the slope of the scatter plot line versus the donut hole parameter. And everything in this column is ray theory, and everything in this column is using the 3D kernels. And what you see is that ray theory starts to systematically depart starts to have this wavefront healing effect and this lowering of the slope right about here when the scale length is about half of the Fresnel zone size. And this dash line here is actually a theoretical curve that we have for this particular diagnostic that I don't have time to tell you about. But we actually have theoretical curves like this for many other wavefront healing diagnostics, and we actually think that in the weakly heterogeneous regime, we really understand basically everything there is to know about wave propagation of finite frequency waves in these media. So here's the bottom line of these numerical experiments in both the one blob model and random media. It is that if you want to recover anomalies that are smaller than this, then you have to use these 3D kernels. If they're bigger than this, you can get by with ray theory. And how big is this? Well, it depends on if you're using 1 Hertz ISC times or whatever. But for Guy Master's data set with periods of 20 to 25 seconds, this scale length beyond which ray theory is no longer adequate is 700 kilometers throughout the mantle. So that's pretty big. And as it says, the answers to many geodynamical questions lie in this presently inaccessible scale range. And the other thing we've learned from these kinds of numerical studies is that what we expect to happen if you invert your data using ray theory is we expect to be able to recover the anomalies in the right place, but they're going to be too low in amplitude. Well, if I had had to give this talk 2 weeks ago, I would have had to stop here. And my conclusion would have been, well, we've got this pretty cool theory, but we haven't really gotten around to applying it to anything yet. But as of 2 weeks ago, we finally have gotten around to applying it to something. What we've applied it to is Guy Master's P-wave data set. And what I'm going to show you are some maps of P-wave heterogeneity in the mantle, which fit his data, which is a small data set, 86,000 data, about 3/4 of which are P-wave times, and 1/4 of which are PP minus P differential times. The inversion was done by Raffaella Montelli, who's a graduate student at Princeton, and she parameterized the Earth model by filling it full of tetrahedra like this, which are roughly speaking 300 kilometers on a side. So that we end up solving 43,000 equations per 86,000 data. And the maps that I will show you, this is very important, I will show you maps inverted using ray theory and maps inverted using 3D kernels, and in both cases the resulting model fits the data to the same precision. In other words, chi-squared is the same. So here is a map at a depth of 900 kilometers. Remember, this is P-wave heterogeneity. We haven't done anything funny with our color scale, as people sometimes do when they show you things like this. This is just a nice linear color scale with heterogeneity going from plus or minus 1.5%. This is a slice at a depth of 900 kilometers. And the bottom is ray theory, and the top is using the 3D kernels. And the way these maps work, if you see something over here and you kind of wonder really what's happening over here to the left, all you have to do is go over here and look at it. It's got a wraparound built into it. So what do you see? Well, the main thing that you see that's really incredibly visible in these models, much more so than in anyone else's models that we've ever seen, including S-wave models, not to mention P-wave models, are all of these red features. These are slow regions in the Earth, 1 to 1.5% slow. And essentially every single one of them is associated with a hotspot. This is Easter Island, this is Tahiti, this is Kerguelen. No, this is Kerguelen. I'm not very good at this, you know. This is Kerguelen, this is Bouvet, this is Cape Verde, this is the Canaries. You can find a lot of hotspots on this. That's at 900 kilometers. This is going down at 1,500 kilometers. 1,500 kilometers, you again see Easter Island, Tahiti, and Hawaii. You also see, as many other people do, you see this subduction of the Farallon plate here and the subduction of Tethys here. This is going on down at 2,100 kilometers. Here the anomalies are sort of the most washed out looking, but you still see these 3 hotspots in the Pacific, Hawaii, Tahiti, and Easter Island. And this is just above the core mantle boundary at 2,800 kilometers. And you still see them, Easter, Tahiti, Hawaii. Here you start to see what people call the Pacific superplume and the African superplume. This is more like the African plus North Atlantic superplume in this case. But these superplumes in this model, which has a much better ability to resolve small-scale features, looks more like what Jerry Schubert in his Francis Birch lecture yesterday called plume clusters. So it really looks like this is a hot region in the thermal boundary layer above the core mantle boundary that is erupting upward in a number of small-scale or smaller-scale plumes. Now, I also want to point out that you actually see most of these features down here in the ray theory model, too. It's just that you see them much more easily up here because they have a higher amplitude. And that's exactly what we expect these kernels to do, is enrich the amplitude of the anomalies. 20 years ago, Tom Crow and Donna Jurdy pointed out this remarkable correlation between the locations of hotspots on the Earth's surface and the large-scale geoid of the Earth with the slab signature removed. And they showed that there's a high region here in the Pacific and a high region here in the North Atlantic and in Africa in the geoid, and that's where all the hotspots are. And we see exactly the same correlation with our hot regions right above the core mantle boundary. I'll show you a few of these cross-sections. The way these cross-sections work is you look up here on the map to see where the cross-section goes, and then you have to look down here, and it's kind of complicated to orient yourself looking at this map here. But this cross-section here is designed to go across a lot of these plumes here in the Pacific. And that's in this region right here. And what you see is this super plume down here on the core mantle boundary, but erupting upward into a number of plumes that you see on the surface of the Earth, including all of these ones that I've put the name by here. And you also see a nice cylindrical plume coming up under Ascension, which is right there. Here's another cross-section. In this case, it's designed to go across these plumes here in Africa. And that's this region right here. You see this cut through the African superplume here, erupting upward into a number of plumes all from the core mantle boundary with these names that I've written next to them. Here is another cut across the African superplume, in this case across sort of more southernmost Africa here. And here is the superplume beneath Africa right here. And this feature here is the one that has shown up in many people's shear wave models, including Jeroen Ritsame's. It's what they call the tilted plume coming up from beneath South Africa and coming up here at Kerguelen right here. But in this model, it actually looks like it also is feeding these hot spots, Cape Verde, Canaries, etc., up here in the North Atlantic. I think I forgot to point out, yes, on this cross-section, you also see a cylindrical Hawaiian plume coming up all the way from the core mantle boundary. Not all hotspots look like deep mantle plumes in this model. Here's the last cross-section I'll show you. It goes through Iceland right here, and here's Iceland. And as in Jeroen Ritsame's shear wave model, it looks like Iceland is a shallow hotspot. So here are some statistical comparisons between these models that we recover using ray theory and banana theory. It's just what we expected. The models look a lot alike. The highs and lows are in the same place. If you measure the cross correlation, it's very high, but it decreases as a function of depth within the mantle, and that's because the kernels get fatter and fatter as you go deeper down in the mantle with these longer waves. This is the RMS in the model plotted as a function of depth, and what you see is that the RMS banana model is more than the RMS ray theory model by about 20%. 20% isn't very much, but this is the RMS. If you instead ask the question, what is the typical ratio of a high or a low in the banana donut model versus the same point in ray theory. And this is a histogram, 2 histograms, sort of in the vicinity of 1,400 kilometers and 2,400 kilometers depth of what this ratio looks like. And the green ones are the ones that are bigger than 1. So almost every place you get this enrichment of the amplitude of the anomaly. And the typical enrichment is about 50%. So here's a last example of this 50% enrichment. This is the one slide I'll show you that has a slightly different color scale, still linear, but now only going to plus or minus 0.9%. And this is the Hawaii plume. This goes absolutely right over it here. And this is the Hawaii plume that you see in ray theory, and you just see it much more clearly if you use the 3D kernels. So it was 30 years ago that our Princeton colleague, Jason Morgan, suggested to all of us that hotspots were the surface expression of deep mantle plumes. Jason is a very circumspect fellow, and you know, he wasn't dogmatic about this. He said it is assumed that hotspots are the surface expressions of deep mantle plumes extending to the lowest part of the mantle. And we've only had this model for a couple of weeks now, and we haven't, and I think the cross sections I've shown you are basically all the cross sections we've actually even plotted of the thing. And this is Rafaela's hotspot checklist showing that these 3 plumes definitely are really deep mantle plumes, just like Jason said, and Iceland is not. And a very natural thing to do is just make a whole lot more cross sections and see what all these other plumes look like. But we are refraining from doing that because the fact is we haven't really, there are a lot of things we haven't done yet. We haven't done any resolution tests or anything like that. By all rights, I probably shouldn't even be showing you this model. This model is not ready for publication. There's a lot more that has to be done. For one thing, it's a pathetically small data set compared to the size data sets that many other people are inverting. And one of the things, the next thing that we want to do is to add ISC data so that we will use very skinny kernels, or probably in fact even ray theory, to incorporate those into the inversion. And that will improve our coverage in the southern hemisphere, because with this small amount of data, there are places where we don't have very good geographical coverage. But our coverage is better than you might think with 86,000 rays, because they're not rays, they're these fat bananas. So this is the Princeton tiger with his new seismological tools. Well, I just want to, this is shameless advertisement, I want to call your attention to 4 papers about this kind of stuff tomorrow. This is a paper at 9 o'clock in the morning by Adam Begg, talking about sort of a technical aspect of these kernels, but we think we actually might be able to put a constraint on basically the spectrum of granularity in the mantle. You can see more pictures of the model that Rafa has produced in Gustno Let's Talk at 9:45, and then there's a poster by Ying Zhu, who has begun a program to compute what finite frequency sensitivity kernels look like for surface waves as opposed to body waves, so that for shear wave heterogeneity we want to be able to use surface waves to constrain the upper mantle like everyone else does. And there's also a talk by Kazu Yoshizawa on the same thing, or a poster on the same thing. So that's all I want to say. I'll thank you for the opportunity to give this lecture. I'll put, this really is my last transparency. I'll put this up and just let you read it. Thank you. It's a little hard to answer that. I think we would have to do some tests, such as measure the travel time for the same waveforms using cross correlation and using your preferred picking technique, and do some comparisons. Because we basically need an equation we can write down that tells us what is this travel time you're measuring before we can design a kernel for it. And so your preferred method of doing this doesn't really have an equation. I should actually say that Guy does it the way you're saying. He actually does not use an automated cross-correlation picker the way Jeroen Ritsema does at Caltech. He actually looks at every single record on the screen himself personally and says, yeah, that's the way I want to cross-correlate these.
One last question. Yes, Tony, could you say something when you have the fine frequency inversions with the late frequency inversions, they have the same price square. Could you say anything about the time of regularization and when it is?
We basically design them to have the same chi-squared and the same wavelength of the anomalies, or scale length of the anomalies. So they both fit the data equally well, and they have the same scale length. And we do apply both norm damping and smoothness damping in both cases. However, we apply these damping parameters, lambda 1 and lambda 2, are much, much smaller in the ray theory case because you get this natural smoothing and damping from the fatness of the bananas. So the models that this is a trade-off curve of model roughness versus model norm, and these are the banana models, and these are the ray models. And the ones I was showing you, I think they're kind of, I actually don't even know which ones they are. I think they're kind of right here in the middle somewhere.
Okay, well, anyway, let's thank you again, and I wanted to present you with the piece of paper.
Great, thank you.
Thank you very much.
Thanks. Yeah. I've got a perfect wall for this.